Welcome back to another HEC-RAS tutorial. In today's session, let's talk about 1D bridge modeling in HEC-RAS and how to set up the bridge opening correctly from scratch. Let's get started here. Before adding any bridge details, the first step is to set up the basic geometry. A good tip here is to build your HEC-RAS model incrementally. Don't add everything at once. Start with the base geometry, check that it looks right, and then add the bridge components step by step. For this example, I have already created the project, named the geometry 1D Bridges, and linked the terrain in RAS Mapper. Now that the base geometry and terrain are set up, let's go ahead and edit the geometry and add the 1D elements. For this demo, I'll first manually draw a short stretch of river reach, following the terrain as closely as possible. Next, I'll draw the bank lines. This will make it easier later to update the bank stations from RAS Mapper at each cross-section. After that, I'll add the flow paths, so RAS has the reach length information for each cross-section. Then we can start drawing the cross-sections along the reach. Since RAS Mapper is geo-referenced, you don't have to worry too much about drawing every cross-section perfectly from left to right. The main goal is to place them correctly across the stream and terrain. While drawing the cross-sections, make sure to include bounding cross-sections around the bridge location, one upstream and one downstream. Once all these elements are drawn in the model, we can update the cross-sections globally, save the edits, and close out of the geometry editor. Next, let's turn on the cross-section river stations so we can clearly identify where to place the bridge. Next, let's move into the geometric editor to define the bridge. Although RAS Mapper allows you to draw the bridge deck line, I usually avoid that method because sometimes the deck line may shift when you exit edit mode, depending on the spacing of the bounding cross-sections. For that reason, I prefer setting up the bridge directly in the geometric editor. Now that the bridge is added, the next important step is entering the bridge deck details in the bridge deck editor. Here we can measure the distance from the upstream cross-section to the bridge deck using RAS Mapper. For the deck width, you can use either as-built plans or survey data, depending on what is available. For this demo, I have an existing bridge drawing, so I'll use the deck information from that plan. After entering the basic deck information, we also need to define the bridge deck profile. A simple way to do this is by using the terrain profile from RAS Mapper. We can measure the distance from left to right across the bridge, plot the terrain profile, and then copy those stations and elevation values into the bridge deck editor. One thing to watch out for here is the 500 ordinate limit. If your deck profile from RAS Mapper has more than 500 rows, the bridge deck editor may only paste the first 500, and the remaining points can be missed. So for longer deck profiles, this direct copy and paste method may not be enough, and you'll need a workaround. A workaround I usually use is to add a temporary cross-section at the bridge location. Then I copy the cross-section profile, just like before, and paste it into the bridge deck editor. The advantage is that cross-sections in RAS Mapper usually use a higher filter tolerance, so the profile is often simplified and stays within the 500 row limit. And since this cross-section is only temporary, you don't even need to save it. After copying the profile, you can simply close out without saving the edits. Now you can see the complete deck profile on upstream and downstream of the bridge. After copying the profile, we still need to clean up the deck line. You may see some low points along the deck profile that don't actually represent the bridge deck. To fix this, select the deck points on the left and right side, then delete the unnecessary points in between. This gives us a cleaner deck profile for the bridge opening. And we can use the copy upstream to downstream option to quickly copy the same deck profile to the downstream side. Next, we'll define the overall bridge opening. For this demo, we'll use the bridge plan to determine the bridge opening width. Then, from the profile plot, we can pick the center line stations for both the upstream and downstream bridge sections. Most of the remaining calculations can then be organized in an Excel spreadsheet for better documentation. For this example, the abutment width is 2.5 feet on each side. So we can subtract the abutment width from both sides of the back-to-back abutment distance to get the actual bridge opening width. Then using the centerline station from the profile plot, we can calculate the opening start and end stations. Simply subtract half of the opening width from the centerline station to get the start station, and add half of the opening width to get the end station. Next, let's insert blank rows at the calculated start and end stations for the bridge opening. Then, copy those stations into the bridge deck editor for both the upstream and downstream bridge sections. After adding the opening stations, make sure to delete any extra stations between them. This is important because the bridge deck table needs the stations to remain in increasing order. Now the next step is to calculate the high chord and low chord elevations. For this demo, we'll use the bridge plan data to estimate these values. In general, the high chord is the top of road plus the parapet wall height, if the parapet can block floodwater. But if the parapet has openings, such as steel railings or decorative gaps, then water can pass through. In that case, use the top of road or deck as the high chord instead. For the low chord, we'll typically use the bottom of the bridge deck. Also remember, the high chord and low chord elevations do not have to be constant. They can vary along the bridge profile depending on the actual bridge geometry. For this demo, even though the bridge plan includes high chord elevations at the piers, I'll keep it simple. I'll use only two high chord points, one at the east abutment and one at the west abutment. RAS will then slope the high chord between those two elevations. This is a simplified approach, and it is usually good enough for approximate studies. Similarly, you can also have multiple low chord elevations along the bridge profile, but here I am going to keep it simple and use one constant low chord elevation based on the conservative lowest elevation from the bridge elevation section. So let's apply that same low chord value to both the upstream and downstream bridge sections. Next, let's add the bridge piers. For this step, we need the pier stationing, pier width, and elevation information, which can come from the bridge drawing or survey data. In this example, the spacing between the piers is 120 feet. So using the centerline station as a reference, we can place one pier 60 feet to the left and the other pier 60 feet to the right for both the upstream and downstream bridge sections. For this demo, I'll assume each pier has a constant width of 2.5 feet, with the pier extending from a lower elevation up to the low chord elevation. When entering the pier elevations, always remember to start from the lower elevation first, then go up to the low chord elevation. Once the upstream pier information is done, you can easily copy it to the downstream. You can also use the copy option at the top left to copy the details from Pier 1 to Pier 2, and then simply update the center line station for the second pier. After adding the piers, always zoom in and review the bridge profile to make sure the piers are properly connected to the bridge deck. The last bridge element we'll add is the sloping abutment. For this example, the bridge has a 2 horizontal to 1 vertical sloping abutment. So we need to calculate the station and elevation coordinates for the abutment slope. The first point will be at the bridge opening start station, with the elevation from the bridge elevation, which is 593.83 feet in this case. And since this is a 2 horizontal to 1 vertical slope, we add the horizontal span to the station of point 1 and subtract the vertical rise from the elevation of point 1 to get the elevation of point 2. Also, when entering the abutment coordinates, make sure the stationing is in increasing order. If the stations are not entered correctly, it can easily mess up the drawing of sloping abutment. After adding the sloping abutment, Zoom in and review the bridge profile carefully. You may notice that the sloping abutment is not fully connected to the bridge face. To fix this, we can add 2 additional stations, one just before and one just after the bridge opening. This helps make the bridge face vertical at the sloping abutment and gives a cleaner connection in the bridge geometry. Similarly, for the right abutment, point 1 will be at the bridge opening end station. The elevation for point 1 will come from the bridge drawing, which is 596.85 feet in this example. For point 2, we subtract the horizontal span from the point 1 station and subtract the vertical rise from the point 1 elevation. Then we can repeat the same process for the downstream side as well. And as mentioned earlier, pay close attention to the order of stationing when entering the abutment points, as stations must be entered in increasing order. The final step is to define the bridge modeling approach. A general rule of thumb is to use multiple bridge computation methods for low-flow conditions when the flow is below the bridge deck, and let HEC-RAS select the highest energy answer as the final solution. For high-flow conditions, when water overtops the bridge, we typically use the pressure and weir flow method. The energy-based method only should be used in special cases, such as when the bridge deck is highly submerged by downstream tailwater and the bridge is completely underwater without acting like a weir. Next, we need to set the contraction and expansion coefficients for the cross sections around the bridge. Per the HEC-RAS manual, these coefficients should be adjusted at sections 2, 3, and 4, which are the cross sections just downstream, just upstream, and one more section upstream of the bridge. In most cases, a contraction coefficient of 0.3 and an expansion coefficient of 0.5 are reasonable starting values. Similarly, we also need to define the ineffective flow areas at the bounding cross sections around the bridge. I personally prefer doing this in RAS Mapper because it allows us to draw the ineffective flow polygons more visually. As a general guideline, we can use about a 1-to-1 contraction ratio upstream of the bridge and a 1-to-2 expansion ratio downstream. For the ineffective area elevation, I would usually set it based on the bridge deck elevation on both sides. It is also a good practice to keep the downstream ineffective elevation slightly lower than the upstream elevation near the bridge. This helps maintain a natural downstream slope and can reduce artificial backwater effects or instability in HEC-RAS. One important thing to remember is that ineffective areas created in RAS Mapper are usually set as permanent by default, but around bridges we generally want to change them to temporary ineffective areas. The reason is simple. Temporary ineffective areas allow the overbank flow to become active once the water surface rises above the specified ineffective elevation. If we leave them as permanent, they can act like artificial vertical barriers and permanently block the flow. That can prevent HEC-RAS from properly representing flow over the road or embankment during larger flood events. So for bridge modeling, make sure to review the ineffective areas and change them from permanent to temporary where appropriate. As we finish up the bridge setup, one final check I like to do is reviewing the bridge deck placement. Make sure the deck is located at the correct position between the bounding cross sections. If it looks slightly off, you can adjust it by changing the distance from the upstream cross section in the bridge deck editor. Then save the geometry to see the changes in RAS Mapper. And that's it for the bridge setup in 1D. Now let's run the model quickly to make sure everything is working. Before we run it, we also need a land cover layer to assign Manning's N values. For this demo, I'll use the NLCD land cover file I already have and associate it with the geometry. Then we'll quickly assign N values for the different land cover types. After that, we can go back to RAS Mapper edit mode and update the Manning's N values globally for all cross sections. Next, let's open the steady flow file and select 3 flow events for this demo. We'll define them as low, medium, and high flow conditions. Then for the downstream boundary condition, we'll use normal depth and enter a reasonable slope value. After assigning the flow values for each event, we can save the flow file, save the plan, and run the model. Once the run is complete, we can review how the bridge performs under different flow conditions. The plan ran successfully without any issues. Now let's open the profile plot and take a quick look at the results. It looks like the initial flow values are still acting mostly like low flow conditions. So let's increase the flows and see how the bridge responds under higher flow events. Now we can see that for the high flow event, the bridge starts to experience pressure flow or overtopping, which is exactly what we wanted to check. We can also review the summary output table from the main window. From there, you can load different result tables to check the hydraulics at and around the bridge. One important value to review is the Froude number. For subcritical flow, we generally want the Froude number to stay below 1, so this is a useful check when reviewing the bridge results. And that's it. This concludes our 1D bridge modeling tutorial in HEC-RAS. If you found this video helpful, please don't forget to like, share, and subscribe. Thanks for watching, and I'll see you in the next tutorial.